We've now seen the limit definition for a vector value derivative or a parametric curve. It's worthwhile thinking about the graphical interpretation of this for a moment, though. Imagine we have a ground point. Here it happens to be of our unit circle moving around counterclockwise and starting at a fixed point of t equals 0.5. And what we studied earlier was the displacement if we travel to another point, say 1.6 in time. Also, if we travel to another point, 0.8. And then we imagine taking smaller and smaller time intervals. Now, it's a bit deceptive to look at the velocity vector on top of this, because the velocity vector is in units of meters per second, whereas this curve, which we defined as r of t, is in units of meters. So in some sense, the lengths of the vectors are not comparable. However, the directions are perfectly comparable because the displacement and velocity are related just by a scaling factor. So the direction stays the same. So if my displacement was in this direction, my velocity will also be in that same direction, average velocity. The nice thing about that is you imagine smaller and smaller time intervals, and what you see is that in the limit, where we take smaller and smaller time intervals, we're going to be getting closer and closer to a tangent line. Because as the points get closer and closer together, we're closer to fitting a straight line tangent to whatever curve we are following in our trajectory. So we formalize that idea. We give it the name the derivative, in case it's not just velocity, but maybe other kinds of derivatives. But the process is identical to what you would have seen before. The derivative is how we write that with the prime notation, is defined as the definition of the displacement divided by, here the h is put to the side for spacing reasons, but it's displacement over the change in time, or the time interval. We see that more clearly in this formulation here, where the delta t is used rather than the more generic h. So this version here is what we explicitly call velocity if r of t is equal to our position. And the nice thing is it's simply the average velocity with the time interval being shrunk down towards 0. Hopefully a question that comes to mind is this related to our earlier derivatives? You've done derivatives before in a single variable context. Well, remember that the single variable context for derivatives was the change in f divided by the change in t, or if you're doing x's and y's, this would be delta y over delta x. But f prime at some particular point a would have been this ratio. Well, not quite that ratio if we're doing derivatives. We would have had, again, a limit as delta t goes to 0 of that. And if we write that out, it's the limit as delta t goes to 0 of f at my start point plus delta t, again highlighting the 2 time points that are relevant, minus the original time value subbed into our function, all over delta t. And if you take a careful look at this versus this, these are identical. The only difference is that instead of a scalar f of t, it's replaced by the vector r of t. Everything you learned about derivatives before is going to get replayed here. Again, maybe with a little bit of novelty, but not a lot of novelty, because the formulation is essentially the same. The only difference is instead of having a single variable to track, we're going to have the multiple variables in r of t to track. If we see how that plays out with an example, we can actually do the derivative calculations and see how it ties into what we have seen before with single variables. We're going to take r of t, and we're going to do the calculation of r prime of t using the definition. That's the limit as delta t goes to 0. And quick correction here, we're going to fix ourselves at some point a, some time a rather, and from the definition we're going to sub in a plus delta t, and then we're going to subtract r of a, and this is again just our end minus the start We're going to take that and we're going to divide it by delta t. Now the limit's usually the last thing we do. We need to simplify these things first. So this defines a trajectory, and we're asking what's the velocity vector at a particular point A on that trajectory. Well, we keep the limit around, and what we're going to do is use our definition of R of t. So we have a formula for it. Let's sub that in and see what we get. So we are going to have a vector here, and it's going to be a plus delta t goes into our function, so a plus delta t. And then for the y component, it's going to be a plus delta t all squared. That is our position after a little bit of time. Then we're going to subtract the position at time a, which is a little simpler. It's simply a and a squared. And all of that divided by delta t. Well, now we have our first challenge with dealing with vectors as opposed to scalars, but we can do a vector subtraction by doing component by component differences. So keep the limit. Calculate the difference between, in the x-coordinates, a plus delta t minus a is just going to be delta t. And then we have this squared. This might take a little bit more work. We'll expand this first. We'll have a squared plus 2a delta t plus delta t all squared minus a squared. And again, all of that over delta t. And we also see immediately that these a squareds here cancel. So if we were to do a naive limit right now, we'd see some possibilities of cancellation, but it still looks like it would be 0 over 0. Having worked with limits before, you would have seen if this is the case of 0 over 0, it's an indeterminate form. You have to go back to the definition, go back to your formulas, do more work, and then try to take the limit again. Emphasize that here. This is indeterminate. And indeterminate just means more work is required. So we're going to do that next. And the opportunity we're going to find is, I'll put everything in blue now, there's a common factor of delta t in everything that remains here. And then we have two a's and a delta t. And all of that over delta t. Again, if we take a limit, it'll still be 0 over 0. But because this is a vector, we have a common factor in each of the x and the y components, which allows us to factor out a common scalar factor, which is a delta t. We take it out of both of these, we're left with a 1 and then a 2a plus delta t over delta t. And now we reach that point where we can actually cancel those two delta t's, numerator and denominator. All of a sudden our 0 over 0 problem goes away. So let's do one last step here. Delta t goes to 0 of simply the vector 1 and 2a plus delta t. Limits ask the question, what happens as delta t gets smaller and smaller, gets closer and closer to 0? Well, it's like adding 0 here. We essentially try to sub it in, and we get just through the limit, evaluating the limit, we get 1 comma 2a, like so. Well, that is interesting, because if you think of your single variable derivative rules, if we had the derivative of t, we would get 1. If we took the derivative of t squared by itself, we would get 2t. If we evaluated each of those at a particular time point, say a, we would end up with 1, 2a, 2a, hey. It feels like we did a whole pile of work here. Good work, important work, but work that we wouldn't necessarily need to do going forward, because at the end of the day, all we did was we took the derivative of the x component. Well, the x component was handled completely independent of the y component. We did all its work separately, and it boiled down to the regular definition of change in x over change in t, which is exactly what our derivative rules give us. Then we did the same thing. We took the y components, the change in y divided by change in t, and that gave us the y component of our derivative. So effectively what we did was we just took the derivative of each component as if it was its own totally separate function. And nothing gets simpler than that in terms of calculus or math. If you know the derivative rules for single variable functions, we can simply take the derivative of the components separately and evaluate them where we need it. So that's our rule for derivatives of vector valued functions. Simply take the derivative of each component by itself using the regular single variable derivative rules, and you are done.